Hello everyone, today let's take a look at quantipose number 42, a pretty cool sets question. So we have a population of commuters. We're told that 80% ride the subway, that's event A, 65% ride the bus, that's event B, and 60% ride a bike, which is event C. Now we're just trying to find the maximum and minimum values of both the triple union and the triple intersection. So for part A, let's bound the triple union, the probability of A union B union C. So we know the triple union of A, B, and C is just by the inclusion-exclusion principle. We add all these up and then we subtract the double intersections and add back the triple. And we know that the probability of A is 80%, the probability of B is 65%, and the probability of C is 60%. So we know that these right here sum to basically 205%. So first of all, how do we make the probability of union between these sets as big as possible? Let's find the upper bound. So this is pretty simple, right? We want to maximize this. We know that this is already fixed, so let's just minimize the terms that we're subtracting off here. And yes, technically we're adding this term back on in our equation, so why would we want to minimize it? Well, you have to understand that these terms are just correcting for overcounting, right? We're actually counting this term in here 3 times. So in the totality of this, we're actually subtracting this term twice. And that's because in this term, we're counting the magnitude of the double intersections twice and the magnitude of the triple intersections 3 times. Okay, so now back to the question. We're trying to maximize this. So obviously we want this to be 0, all of these terms to be 0. We want 0 overlap. Okay, so if we make these 0, then the probability of union would be 205%, but we know in a probability space that you can only at most have 100% total, right? So all that means is we're guaranteed to have some type of overlap, but if we wanted to put a bound on this, well, it's going to be less than the magnitude of the entire probability space, obviously, so less than or equal to 1. Also, obviously super easy to visualize. I have event A that needs to take up 80% probability mass, and then I have event B or C that I could place in the remaining 20%, and it's going to occupy the whole space. Also, the lower bound for the union will be pretty simple as well, so let's do that. Okay, so now we want to minimize this union, and we know that this is 205%, so let's make these as big as possible, the terms that we're subtracting off, which are the intersections. And yes, even though this says plus, in this entire term, we are net subtracting it 2 times, right? So this is a little bit misleading, so I'm going to rewrite this. So let's just call the entirety of that the intersection terms that we're overcounting in here. So if I want to make this as small as possible, I want to make the amount of overcounting in here as big as possible, so we end up subtracting the most, right? So how do I do that? Well, it's pretty simple. I just take event A and then I place event B in it. That'll maximize the intersection between them. And then I'll take event C and I'll place it inside of that. And now what's the probability of union? Well, it's just going to be the magnitude of my biggest circle, which is event A, 80%. So this is going to be lower bounded by 80%. Also, if you actually wanted to solve this equation, this is what the maximum intersection terms would be, right? This is the maximum triple intersection. This is the maximum double intersection between event A and event B. And then this is the maximum between A and C. And then this is the maximum between B and C. So if you took 2.05 and subtracted off these terms and added back this one, well, then you'd get 0.8 as well, right? Also, maybe the best way to think about this is imagine that you have 205 different commutes total. We're representing this percentage as a number now, so we know that we'd have 100 total people if we were looking at it like this. So we're trying to lower bound the union, so we'd want to overcount in here as much as possible. And we know that triple intersections count 3 times in here, right? So first I'll make my triple intersection as big as possible, and the biggest I can go is 60 people, the size of our smallest circle. And then that would contribute 3 times 60, 180 to this total number. Now, since I've maximized the number of commutes that contribute 3 times to it, right, it would be all of this black area in here. Now, the next best thing I could do is just to maximize the remaining double intersection. So this blue one was event B, 65%. So there'd be 5 people remaining out here that only are in the double intersections and not in the triple intersection. So these 5 people would now contribute twice to this total. And then there's no more overlap available, so I'm just going to have to add on the remaining of this, 80% minus 65, which is 15. So I'm going to count those 1 time each. So 15 people get counted once. So that's the best I could do, right? 60 people were counted 3 times, 5 people were counted twice, and 15 people were counted once. And when we sum those up, we get 80% again. Yeah, sorry to make that so complicated, but basically the main thing is just look at the Venn diagram and it's pretty simple to figure out, right? Now let's look at part B, where we're bounding the probability of intersection between A, B, and C. So to upper bound this, it's going to be really simple. Obviously, it's just going to be equal to the event with the smallest probability mass, because then we can overlay the others on top, and the triple intersection can't ever exceed the magnitude of its smallest bubble, right? Now the probability mass of the smallest event is event C with 60%, so this intersection is bounded above by 60%. Now probably the hardest part out of any of these is the lower bound for this. Okay, so we know that the sum of the probabilities is 205%, but let's just think about it as the number 205, and we have 100 total people in our probability space. So we want our triple intersection to be as small as possible. So what does that mean? Well, we want to maximize the contribution to this term from our double intersections and our single intersections, right? So we minimize the contribution from our triple intersection. So I need to maximize the contribution to this from my double intersections because those are going to count twice, which is the highest number if we're trying to minimize triple intersections. So the best I can do, well, I have 100 total people in my probability space, right? So what I need to do is make all of them have double intersections, right? And that'll maximize the number of double intersections for this probability space. So when I take 100 times 2, I'm contributing 200 to here. And if everyone's a double intersection, then no one's just going to belong to one event, obviously. So if I get all my contribution from doubles, I'm going to have 5 events left that I need to distribute, right? And that just means that we need 5 out of these 100 people who are already contributing twice to contribute one more time and go into the triple intersection, right? So even when we maximize the double intersections, we're still going to have 5% of people that must be in the triple intersection. So that's going to be our lower bound. Also pretty simple to visualize. Imagine I have event A that needs to take up 80% probability mass. Then I want to maximize the double intersection. So now I want to add on either B or C. It doesn't matter. So let's say I add on event C such that it takes up the remaining 20% over here, and then it's 60% total, so it needs to occupy 40% of A as well. So now this green and blue overlap region will be the overlap between A and C. So this overlap here is 40%, and I still need to add on the event B. So B is 65% of the total probability mass, and I want to minimize the amount of triple overlap, right? And if I add B to this region here, well, then I'm going to get triple overlap. So I want to add as little B to this 40% as I possibly can. So B is worth 65%. There's 60% remaining that would not give me triple overlap. So I'm going to add as much B as possible to this region. So I add 60% of B to the single overlap region, but I still have 5% of B left. So I have to add it to this region here, which is going to make 5% triple overlap. So again, the lowest I can get this number is 5%. I also didn't mean this video to be so long. It's actually not that hard to solve. You can just look at the Venn diagrams mainly if you want to solve this, but I was just trying to add in as many ways to solve it as possible.